Hi everybody. This is our lecture on section 4.5, which is on the chain rule. Recall the chain rule from single variable calculus. Right? Given a composition of functions, f of g of, and let's put a t inside here. F of g of t, and we want to take the derivative with respect to t. Well, that's equal to, if you remember, I'm sure you do, f prime of g of t times g prime of t. Let's rewrite this in differential notation. Rewriting this in differential notation, when y is equal to f of x and x is equal to g of t, right? So you have the function y up top, and y is ostensibly a function of x, but since x is a function of t, y is ultimately a function of t, right? So when you write f of g of t, think of y is equal to f of x, and then x is equal to g of t, without sticking the g straight in there. So now, d over dt of f of g of t is equal to f prime of g of t times g prime of t. This becomes, okay, well, here we have the function z, y equals f of x. Yeah, dy dt is equal to, well, what's this? Y is f of x, so that's f prime of, and the g of t is x. So f prime of x, so that's dy dx. And this, g prime of t, is dx dt. Right, so this is y of t. This is f prime of x, and this is g prime of t. So this is dy dt, and this is dy dx, dx dt. Notice that, if you take this sort of idea where you can cancel differentials, then this has the effect of canceling out the dx's and just coming back to dy dt. Right, so it's got a nice, neat form. Now, with multivariable calculus of the multivariate so there's many different forms of it, but they're all similar. Given z as a function of two variables, f, x, y, and x is equal to a function of t, and y is equal to a function of, not f, of t as well. So given z as a function of x and y, but x is a function of t and y is a function of t, just like this sort of situation up here. Okay, we get that z is ultimately a function of t, right? We have the function z on the top, and z is written in terms of x and y, and then x and y are both written in terms of t. So we've got this tree structure here. The chain rule states because z is a function of t, you can take the derivative of z with respect to t. Single variable derivative, dz dt. Well, that's equal to the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. So z gets partial derivatives in terms of x and y both get ordinary derivatives, dx dt and dy dt. So it mimics this here, right? Except it's got a sum. So dy dt is dy dx, dx dt, where you're going down this tree structure here. Here we have dz dx, dz dx, dx dt, plus dz dy, dy dt. So it looks like that. And we can actually prove this is true. Proof is not too difficult now that we have this concept of the differential from before. So a sketch of the proof of the chain rule. Okay, by definition, dz dt is equal to, well, it's the limit as delta t goes to 0, the change in z over the change in t. Yeah, I know it's it's f of t plus h minus f of t over h. This fancier way or more specific way of doing it. But what it is just this represents a change in t, because t goes from t to t plus h, so h is the change in t, and z is the change in f. So it's just change in z over change in t. Using the form of the differential, as an approximation, right? The approximation for delta z by the differential, it works really well for small changes around z, which is exactly what this is, a change that's approaching 0. Delta z, we now get that dz dt is equal to the limit as delta t goes to 0. Dz is the partial z with respect to x times delta x plus the partial of z with respect to y, delta y over delta t, which is equal to the limit as delta t goes to 0, and let's just distribute the numerator over the denominator, delta x over delta t plus partial z with respect to y, delta y over delta t. Well, these partial derivatives are constants, and we have the limit as t goes to 0, as delta t goes to 0, change in x over change in t, plus dz dy, the limit as delta t goes to 0, change in y. Oh, this is a delta y over delta t. Well, the change in x corresponding to this change in t is, by definition, dx dt. And the corresponding change in y, given the small change in t, as the change in t goes to 0, is, by definition, dy dt. So this is, by definition, dz dx, dx dt, plus dz dy, dy dt. And that's what we were looking for. So let's take an example. Let's take an example. So let's say z is equal to, just something simple, x squared y to the third. And x is equal to the square root of t. And y is equal to t squared. Something like that. Therefore, z is equal to the square root of t squared times t squared to the third. So that's equal to t times t to the 6th is t to the 7th. Right? So, well, dz dt is then equal to 7t to the 6th. Now let's calculate by the chain rule. dz dt is equal to dz dx dx dt plus dz dy dy dt. So this is equal to, well, dz dx is 2xy to the third. And then dx dt is 1 over 2 square root t. Plus dz dy, partial derivative of z with respect to y, is 3x squared y squared. And then dy dt is 2t. Right? So that's the the derivative dz dt in terms of x, y, and t. But of course, x and y are functions of t, so you can just write them out. So this is equal to 2, and then x is square root of t. Y is t squared, so that's t to the 6th, over 1 over 2 square root t, so those cancel, plus 3t, t to the 4th, and then times 2t. So this is equal to t to the 6th plus 6 t to the 4, 5, 6, which is 7t to the 6th, same as before. See that? Now, normally when you need the chain rule, you don't typically have this kind of information, or maybe it's going to be enough information to just calculate it this way, or maybe it's going to be inconvenient to do so. I mean, you need the chain rule in many instances like this. Other forms of the chain rule. Oops. So, I mean, say we've got a 3-variable function. Say w is a function of x, y, and z. And x is a function of s and t. Y is a function of s and t. H of s, t. And z is a function, g, h, I, j, k, s, t. So w is a function of x, y, and z. So you have w on the top is a function of x, y, z. Immediately. That's the first layer of variables. And then x, y, and z are both functions of s and t. So you've got this tree-like structure here. So w is a function of s and t, right? Ostensibly, it's a function of x, y, and z, but ultimately, it's a function of s and t, right? So you should be able to take the partial derivative of w with respect to s and the partial derivative of w with respect to t. So there's the chain rule for both of them. So dz partial z with respect to, not w, s, dz ds go down the tree to s, w to x to s. So dw dx dx ds, dw dx dx ds. And now it's all partials because there's no ordinary single variable functions going on here. Everything is a multivariable function, so it's all partial derivatives. Now go down the tree from w to s. Dw dy dy ds. Dw dy dy ds. And then dw dz dz ds. Dw dz dz ds. And so that's dz ds. And then dz dw, just the same. Okay, that's dz ds. So for dz dw, get rid of the s's and replace with w's. So dz dw is dw, or dt, dt, dz dt is dw dx dx dt. dw dy dy dt. dw dz dz dt. dw dz dz dt. So the only difference between these two expressions, this has got s, 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 t, 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 t. And, you just get that expression by going down the tree from top variable to bottom variable in all the different ways. wxs, wys, wzs. wxs, wys, wzs. All right? If you remember implicit differentiation from Calculus 1, so recall that if we have a mixed equation of x and y, then, right, consider x as an independent variable considering x as an independent variable, we then have that y is a function of x, not explicitly, but implicitly. Right? It's not explicitly a function of f, but implicitly a function of f. So, right, so we find we find the derivative dy dx by applying d over dx to each side of the mixed equation, right? If you remember how that goes, suppose we had x squared plus xy plus y squared equals 1. So then you apply the differential operator d over dx to each side. Derivative with respect to x of x squared is 2x. The derivative with respect to x of x times y, using the product rule, right? The derivative of x is 1 times y plus x times the derivative with respect to x of y, which is dy dx, plus the derivative with respect to x of 2y, right? Using the chain rule of y squared is 2y times the derivative of the inside, dy dx, and over here it's 0. Right, and then you solve for dy dx. So dy dx is equal to minus 2x plus y over x plus 2y, right? But you can do this instead with implicit differentiation, or with the chain rule. This can be done with a chain rule as follows. 1, set the mixed equation to 0. For x and y equal to, right, move everything to one side of the equation. So call the non-zero side f of xy. So just some big old function, f of xy. Right? So now, we'll have to call it z of xy. Call it z of xy. So now we have, right, z on the top. Z is a function of x and y. X is a function in terms of itself, and y is implicitly a function of x. Right? So z is ultimately just a function of x. X is a function of itself, and y is implicitly a function of x. So dz dx is equal to dz dx 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 dz dy dy dx. All right, now z is a constant. Right, call the non-zero side z of xy. Thus, z of xy equals 0. Right, you start with your mixed equation for x and y. Set it equal to 0. Right, so then call that mixed non-zero side z. So then z of xy is equal to 0. And now you have z, which is 0, but just think of it as a function z, is a function of x and y. X is a function of x, and y is implicitly a function of x, so we got that. Since z of xy is equal to 0, dz dx is 0. And, of course, dx dx is 1. Thus, 0 is equal to partial z partial x times 1 plus partial z partial y dy dx. So, dy dx is equal to the negative partial z with respect to x over partial z with respect to y. So going back to that same example, where's that example we had before? Right there. Right? You can set it equal to 0. Actually, you could set it equal to any constant because the derivative of any constant is 0. But, you know, I mean, we'll follow the technique we said minus 1 is equal to 0. So, zxy is equal to x squared plus xy, x squared plus xy, plus y squared minus 1 equals 0. Right? So, dy dx is negative partial with respect to x. Partial with respect to x is 2x plus y plus 0 over partial with respect to y, x plus 2y plus 0 plus 0. Wow, nice. Right? I mean, it's just taken a couple partial derivatives and we got the same answer, right? Same answer as before. So, when you have that mixed equation with x and y, and you want to find dy dx, instead of using implicit differentiation, you can just do this. Push everything over to one side. There's your function z. dy dx is partial z with respect to x over partial z with respect to y, negative of that. And you can do the same kind of thing with multivariable equations as well. Okay? All right, so that's the end of the lecture on section... Oh, no. I got one more example I want to do. Yes. Yeah, this is nice. So here's a applied example. So suppose you have an electric circuit. Okay, here's some sort of voltage source. You've got a circuit. It's got a voltage source, and then it goes through some resistor, and then goes back to the voltage source. Okay, Ohm's law states that, you don't really even need to understand it, just Ohm's law states that the voltage of the voltage source is equal to I, that's current, so voltage in volts, current in amperes, amps or amperes, times R, resistance in ohms. The voltage drop across a resistor satisfies V equals I times R. Supposing that you've got some sort of simple resistance circuit there, supposing that the resistor has a resistance of 400 ohms, right, and the current is 0.1 amps, and the voltage dV dt is changing at minus 0.01 volts per second, and the resistance is changing at 0.03 ohms per second, right? And the voltage is no, I'm sorry, no, the voltage is changing as well. So we've got a resistance of 400 ohms, a current of 0.1 amperes. Then you get dV dt, change in voltage. It's going down slightly per second, and dR dt is going up slightly per second. Find di dt, the rate of change of current in amps per second. Right? Well, what does the chain rule say? I mean, what sort of setup do we have? We're doing everything in terms of a time parameter in seconds. Right? We've got a voltage function, V, is written in terms of current and resistance. And then current and resistance are varying with respect to time. So this is the same kind of setup that we got in Calc 1 when we were doing those related rates problems, if you remember that stuff. So those related rates problems, they become a lot simpler when you look at it using the chain rule. So here, di dt is equal to, or dv dt is equal to di dt, no, dv di, dv di, di, okay, dv di, di dt, plus dv dr, dr dt. Right, you're using partial for the derivatives for v, because v is in terms of I and r, but I and r are just in terms of t itself. So that's the ordinary derivative. Okay, dv dt is minus 0.01. Partial v with regard to dv di. Partial derivative of v with respect to I is just r, right? dv di is just r times di dt, that's what we're trying to find, di dt, plus dv dr, partial derivative of v with respect to r is just I, which is 0.1 amps. We'll just put I here for a second, times dr dt, 0.03. Right, so minus 0.01 is equal to the resistance, 400 ohms, times di dt, plus I, the current, which is always 0.1 amps, times the rate of change of resistance, 0.03. So we have minus 0.01 minus 0.003 over 400 is equal to di dt. And that is minus 0.013 divided by 400. So 0.0000325. So amps per second. So the rate of change of current is going down slightly at that many amperes per second. Okay, so that's the end of the lecture on this section.